He received his PhD from the University of Michigan, Ann Arbor in 1990. He is currently a professor in the Department of Ecology, Evolution, and Behavior in the College of Biological Sciences at the University of Minnesota. He has published over 100 peer-reviewed publications, including studies on characterizing bacterial communities and carbon and nutrient cycling and how they all interact to regulate production and decomposition in aquatic systems. And today, he's going to be talking about carbon sequestration, as it is an important ecosystem function of wetlands and can differ between wetland types and may be impacted by changing climate and rising levels of carbon in the atmosphere. Today we're going to learn what recent science says about how we can restore and manage wetlands for carbon storage and about the potentials and limits of carbon sequestration in wetlands. So without further ado, thank you so much for being here, Jim.
Okay, thanks, Christine. Well, most of that I'll talk about. I may miss a couple of things. Okay, so it's great to be here. I love talking about wetlands, and before I forget, I wanted to mention, so what I'm going to talk about today is some work we've been doing looking at alternative stable states in wetlands and how that affects carbon burial in wetland systems. The take-home lesson, I'll tell you right off the bat, is the alternative stable states don't seem to matter all that much. But what we have found is that all these prairie pothole wetlands that we've been looking at seem to bury an incredible amount of carbon, and that's an important thing. So from a management perspective, the main thing is to keep your wetlands. There are other reasons to manage for the clear state versus the turbid state. And if you don't know what that is, I'll talk about it. But basically, the clear state is having lots of macrophytes in the wetlands. Okay. But before I forget, I wanted to mention one other thing that is very management oriented that we've been trying to do for a few years, and we've had a little bit of success in terms of management of wetlands. And I've been working with the DNR on this, and they're very interested in developing more management tools for wetland systems to get them to switch basically from the turbid state with lots of algae growing to the macrophyte dominated state. And one of the things we explored a few years ago was adding CO2 into lakes underneath the ice, because if you can add enough dry ice, basically it asphyxiates fish. And if you can asphyxiate the fish, then often without the fish in the springtime, it tends to switch closer back into a macrophyte dominated state, because the fish tend to promote more of the phytoplankton growth. I'm not going to talk anything about that, but if you had questions, I'd be happy to entertain those at the end. So here's the agenda I'm going to try to work on today. So we'll just discuss the role of lakes and wetlands in the global carbon cycle. A lot of my work is focused on larger lake systems, but I see wetlands as sort of part of the continuum, going from smaller systems into larger systems like the Great Lakes that I also work in. We'll talk about some of the mechanisms that seem to be important in terms of burial of carbon and sequestration of carbon in freshwater systems. We'll examine these processes specifically in prairie pothole lakes, because that's where I've mostly been doing my work. And then finally we'll finish and talk about the management implications of that. So the questions specifically focused on the prairie pothole work that we've been looking at is how much carbon is buried in those systems, okay? We're also interested in whether or not systems can bury dissolved carbon. And I'm not going to talk at all about that today with you, But the take-home lesson is that they can, but it's relatively insignificant relative to particulate matter, right? Because, well, yeah, actually I will address it a little bit again. And then how much production occurs in these systems, because the production basically is the key to everything, because that's where the carbon is removed from the atmosphere and put into the system in a reduced form. And then as far as mechanisms go, we're interested in how much oxygen matters. So oxygen is important for a number of reasons. One is because when it's present, respiration rates can increase significantly. So aerobic respiration tends to be faster than anaerobic respiration processes. Another reason it's important is because if you have oxygen, you also have animals that can burrow down into the sediments and increase the oxygen exposure of material that's already been buried in the sediments. Okay? And they can also munch on organic matter, and that helps break it up as well. Okay. So, before we get started, I thought I would give you a little quiz. So, get out your pen and paper, if you have it. Or if you remember, that's fine too. So I'm going to start here, just to get an idea where my audience is. So, what is a gigaton? And I will tell you off the bat that a gigaton is the equivalent of a petagram. Does anybody know the answer to that question? If you do, raise your hand, and you'll get an extra cookie at the end. So I'm not just asking this because so I can show to you that I'm smarter than you, because I know that's not the case, but it's an important measurement of carbon burial on a global scale, and that's why we need to know what it is. So it is 10 to the 15th grams, okay? So a gigaton or a petagram of carbon is 10 to the 15th grams of carbon, okay? 10 to the 15th is a hard concept for most of us to grasp onto. The best way that I can think to explain it to you, Chris Sabine, who's with NOAA, explains it this way. So if you took 10 to the 15th grams of coal and put it on a train, you could take, that train would wrap around the equator 60 times if it had a petagram in there, okay? So these are big numbers, okay? And, you know, when you're dealing with big numbers on the Earth and trying to measure them, there's probably a lot of error associated with them. So keep that in mind. So how many petagrams of carbon do humans release to the atmosphere every year? Anybody know what that number is? So that would be 600 trains of coal, basically. So 10 petagrams is the way that humans are perturbing ecosystems, or particularly how we're perturbing the atmosphere in terms of releasing CO2 into the atmosphere. So that's the number that we need to start with, because that puts everything else in context. Okay, so our CO2 in the atmosphere is increasing at a rate of about a part per million per year at this point in time. Okay, and that amounts to 10 petagrams. Okay, and that's what we need to deal with. And in terms of management, that's the number that we have to sort of figure out a way to get rid of it, essentially. And the last question, are freshwater is important? This is the freebie question that everybody gets right, of course. I'm talking to you about freshwater, so of course they're important. This is when I teach a course at the U called Biogeochemical processes, which the way I explain it to my people that ask me about it is it's essentially trying to understand the whole Earth in terms of as an ecosystem, right? So if you change some process on the Earth, how does it change the behavior of the Earth as an ecosystem, okay? And again, putting the carbon cycle in context, this is a very simple model of the global carbon cycle, okay? So there's lots of arrows here. Those arrows represent processes or fluxes. And if you look up there at land plants, it says 560. So that means there's 560 petagrams of carbon that are in land plants on the Earth, if you add everything up, okay? That's a huge number. But a lot of that biomass is turning over fairly quickly. So 120 petagrams come into plants every year. So that's the rate of carbon fixation. But another 60 petagrams comes out through respiration just by the plants, okay? The rest of it, if you look at the soils, is lost from the soils as respiration. So that would include microbes in the soils, and that's mostly where the decomposition occurs. But it would also include animals that are feeding on material that's produced by land plants as well. Okay? So it's pretty close to being in balance, but I'll show you that it's not quite perfectly in balance. Same kind of things happening in the oceans. But in the oceans, it's a little bit different. So in the oceans, there's photosynthesis, and there's decomposition. They're pretty close to being neck and neck, so they're pretty balanced. But you can also see there's more carbon coming into the oceans than's going out, okay? And the way that works in the oceans is, let's go back to the 10 petagrams. So the 10 petagrams come over here. So this factory is representing fossil fuel burning. So that's about 9.1 petagrams. And then by land clearing, another 0.9 petagrams of carbon is released into the atmosphere as CO2. So that's our 10 petagrams. And the question is, where do those 10 petagrams go? They have to go somewhere, right? Well, 5 of them accumulate in the atmosphere. And that's, again, the great experiment that I talked about. Another 2.5 or so dissolve into the ocean, just as dissolves CO2, okay? And then the rest, we think, is going into land plants, okay? And eventually into the soils, okay? So that pretty much balances it. So the question is, where's fresh water in all this? So all the biogeochemists, they look at this and they don't need it, basically, in order to balance it. But thankfully, a few limnologists a few years ago wanted to be relevant, so they started to look at it, okay? And they started with a very simple question: does fresh water matter? And the construct they used to talk about this is called the pipe model. So the top diagram there basically shows a null model. It says, basically, we know if you look at that number on the right, 0.9, that's the amount of carbon that's transported from land to the oceans every year. And that number is pretty well known. If inland waters don't really matter from the carbon cycle perspective, then basically they take that 0.9 petagrams from the land and they transport it directly to the oceans. Well, of course, we know that's not true. We know that stuff happens, you know. We grow fish, we grow plants in freshwater systems, we grow peat, lots of things happen. And so that's sort of what's depicted in these two models here. And the only difference between the middle model and this one is that they were done at different times with probably better numbers in this paper. And I'm also a co-author on this paper, so I know it's better. But what we came up with was basically almost 3 petagrams come into freshwater systems from the land. 0.9 goes to the ocean, like we said up above in the passive pipe model. But these are the pools that sort of make up the difference between this and this. And so this release here is CO2 that's respired. So the organic matter that comes into fresh waters is respired and turned into CO2 and returned back to the atmosphere. So about half of what comes in is released that way, and 0.6 petagrams is actually buried into the sediments of freshwater systems. And that 0.6 is really important because once material gets buried in sediments, it can stay there for a really long period of time, on the order of hundreds to thousands of years. And so in terms of our lifetimes, that's a real important thing, because that means we've successfully removed some of that CO2 from the atmosphere and put it away for a long period of time. Okay. So in order to sort of quantify the freshwater role in these kind of things, a lot of these same scientists decided, well, if we want to know what freshwater systems do, and in particular lakes, they said we need to know at least, we need to start by knowing how many lakes there are on the Earth's surface. And so John Downing and a lot of the guys that were on the coal paper tried to put together a model to come up with this. And they basically came up with this model. So on the y-axis is lake frequency, and then on the x-axis is the size of the lakes, the lake area. So what this says is we have a lot more small lakes than we have large lakes. Okay, and the fact that these small lakes are, if you get small enough, they're basically wetlands. Okay, and that's one reason why it's relevant to you guys. But when he quantified all this, there's over 300 million lakes on the Earth's surface. Okay, and I asked him one time how many of those lakes are actually in Minnesota, because it's a regional model, and so he can actually calculate for different regions what the number of lakes are. Because of course there's a lot more lakes here than there are, say, in the Dakotas, right? So it has to be regional. And his number is over 4 million for Minnesota. And that's important because we mostly think of lakes as 10,000, right? So, but that 4 million number, A, is pre-settlement, pre-European settlement, and also before we drained a lot of wetlands. So the number today would be much less than that. But again, it also demonstrates to you the scale at which he's counting things as being lakes. I mean, most of the time people use, I don't know, 10 acres or something as the lowest value for a lake, but he went much smaller than that. So what do lakes and small lakes and wetlands actually do? And this is important because if we want to look at the role of these systems in the carbon cycle, we have to know basically how much carbon they're taking in every year. Okay? So this is just a figure I took out of an ecology textbook. And so if you look up at the top, there's estuaries and then swamps and marshes. And the numbers here are average net primary productivity. So the amount of kilocalories, if you put it in terms of carbon per meter squared per year. And you can see that wetlands basically are at the top of the scale, suggesting that they could play an important role in terms of removing CO2 from the atmosphere. And they do. So what does it mean to matter in terms of the carbon cycle? I think we've kind of hit on this already a little bit. So we have all this excess CO2 in the atmosphere. It can either be taken into the system, so that the downward arrow represents photosynthesis, or it can be respired out of the system as respiration or decomposition. And then what's left over ends up in plants and other organisms, or it can end up down here in the sediments. Okay? And what we want to be happening in these wetland systems is basically for material to be accumulating here, and particularly we want it to accumulate down here, because this material, once it's in sediments, it's going to be there for the most part for a long period of time. Okay? In effect, what we've done then, by going from up there down here, is we've removed CO2 from the atmosphere for a long period of time. To put this in context, Eva Gorham from my department and Walt Dean from USGS, well, it's over almost a decade ago, almost 20 years ago, published this paper. It's one of the first ones where people started to think about the role of fresh waters in terms of the carbon cycle. And they did their best job to quantify the area. This is before the work of John Downing. But they also quantified the burial rates. So this is the amount of carbon that ends up in those sediments in a given year. And so the numbers are quite variable. But you see that large values are associated with reservoirs, which we didn't have any clue that they could bury so much carbon before this paper was published. And also small lakes and wetlands, okay? So, and if you put the area and the burial rates together, you can get these numbers over here, which is a measure of the total amount of carbon that's buried in those systems. And what was really surprising in this paper is if you compare organic carbon that's buried in all inland freshwater systems to the oceans. And now soils were not included in this. What you end up with is about 0.3 petagrams in freshwaters compared to about 0.1 petagrams in the oceans. Now, first of all, 0.3, we now know that that number's probably double that. So this was done before the Tranvik paper came out. So we know that that number in freshwater is even higher than what we first thought. But the other thing to keep in mind is this number for the oceans of 0.1 petagram, that's not the way that the oceans remove most CO2 from the atmosphere. Mostly they remove CO2 from the atmosphere by the CO2 directly dissolving into the water. This is only referring to the carbon that's being produced through photosynthesis that ends up getting buried in the sediments. Okay? Those are two different mechanisms. Okay. So to sort of bring it home and tell you a little bit about our work in Prairie Pothole Lakes, this is a map showing the stars, basically the systems where we've been working in out in western Minnesota. The Prairie Pothole region is huge, 900,000 square kilometers, about, in terms of surface area, about 23% of that is actually wetlands. And it's being converted more and more every day to farmland, basically. This is a picture of a couple of our lakes outside of Fergus Falls, and I mentioned these two different states. You can see it from this aerial perspective. Basically, the clear lakes are at the top, and one over there on the right, are dominated by macrophytes, and the turbid lakes are dominated by phytoplankton. And you can clearly see the difference in those two different systems. This is a closer look. You can also see that the plants differ quite a bit. So one way to look at their role globally is to look at how much carbon is buried globally in these systems. And this paper came out about a little over a decade ago, actually quantified this for different kinds of systems across the world. What we have here is the carbon burials way up there at the top, and the area is right underneath that. So wetlands, even though they only, they represent, in terms of this diagram, they represent a very small portion of the total area. In terms of the total amount of carbon buried, they're very significant. And so that's one of the motivations for why we were looking at these pothole systems in the first place. but there's a lot of variation. Okay, this is looking at carbon burial in grams per meter squared per year across lake area. So our wetlands are way down here in this region. And you can see by looking at these data, so this is a log scale, that the wetlands basically differ by about 4 orders of magnitude in terms of carbon burial. And so one of the questions we were trying to address in our work was, why is there so much variability? What are the mechanisms that really lead to all that variation in carbon sequestration? And one of the things we thought might be important is just exposure to oxygen. So in Hillary Hartnett's work in the ocean, so this is open ocean sediments, she looked at how much oxygen exposure a given amount of sediments is exposed to during its lifetime, basically. So when material falls down, the fresh organic matter is at the top, and when, in most of the ocean, when it falls on the top of previous sediments, it's aerobic. There's oxygen there, okay? As time goes on, more and more material piles on that organic matter, and eventually it becomes anaerobic, okay? And so if you know the burial rates, and you know the depth at which oxygen penetrates into the sediments, you can basically calculate the number of years that that material is exposed. And if you also know the rate at which material falls down onto the sediments, you can calculate the burial efficiency, which is basically what percentage of what falls in the sediments actually ends up getting respired. Okay? So higher efficiency means more of it remains in the sediments. And she found this negative relationship. So more oxygen exposure, and the scale here is going from, a few weeks up to 1,000 years. So there's a lot of variability in the oceans. Negative relationship suggests that oxygen might be an important factor in terms of degradation. Sebastian Sobeck, in this paper that came out more recently, basically found the same thing. This is in lakes, okay? But he found essentially 2 different lines. They're both negative, like we saw in the previous diagram. But what his work showed is that lakes that are dominated by external inputs up there at the top bury material more efficiently than lakes that are dominated by in situ production. So these are mostly large lakes. Okay, and it's consistent with the other material I showed you, suggesting that small lakes are really good at producing carbon, but they're also really good at burying carbon. So we decided to look at this in our wetland lakes out in the Pothole region. And so this is just showing you how we do this. So these are microelectrodes that we put into cores. So this core, we basically push it down into the sediments and we pull it up. And when we look in the core, basically the material at the top is recently buried material. You can even kind of see in this one that it's kind of green, so it's fresh. And then as you go back in time, as you go deeper, you get more older material. Okay. So this could be, pre-European sediment that's down a few tens of centimeters. Okay. And then these are oxygen and pH probes that we put in there, and you can measure very small increments of change in oxygen as you go deeper and deeper into the core, so that we can calculate the oxygen exposure time as long as we know the rate at which the sediment is accumulating. Okay. So we did find that there were some differences. They're not huge differences in the clear versus the turbid lakes. Okay. So oxygen extends further into the clear lakes than it does in the turbid lakes. And that's kind of what we would have expected, because one of the things that the macrophytes do, they can inject oxygen directly into the sediments through their roots. So that's one thing. And the other thing that's important is in the clear systems where you have macrophytes, more light reaches the sediment surface. And so you can have photosynthesis occurring right at the sediment surface, and that can increase the oxygen injection, basically, into the cores or into the sediments. Okay, but I mean these are millimeters, so we're only talking, you know, tiny little bit. These differences actually turned out to be significant difference, and this one and that one are significant as well, but not these two. But one of the questions is, it may be statistically significant, but is it biologically significant? So does oxygen really play an important role in terms of how much organic matter gets buried in these systems? Another way to look at oxygen, so DO refers to dissolved oxygen, is we look at oxygen underneath the ice in the winter time. So most of these lakes go anaerobic at some point in the winter, particularly if you get a winter that's very cold, so you get ice on the lakes for a long period of time, and you get a lot of snow that piles up, because that will decrease the light that extends down in the sediments and decrease the amount of photosynthesis. Because the only way to produce oxygen when there's ice on the lake, you no longer can get oxygen from the atmosphere, you must get it through photosynthesis. And basically what you see here is that not always, but in the turbid lakes, the oxygen tends to extend almost into February in those systems. Whereas in the clear lakes, where you have angiosperms, the oxygen usually is gone by early January. Okay, so this suggests that, you know, there may be more oxygen exposure in these phytoplankton-dominated systems, and therefore you're not likely to accumulate as much organic material in these systems. But I'll show you later on. So far, we haven't really been able to detect much difference. Actually, it's in this slide right here. So what we're looking at here, so these are different lakes. So these are the names of the different lakes. Some are turbid, some are clear. So these are the macrophyte systems over here. And then the different colors represent, so this was before European settlement, this is 20th century, and then this is post-1995. Okay, so before European settlement, a longer period of time during the 20th century, and then this is the very recent stuff. And for the most part, all the lakes show the same pattern, where you have lower accumulation in the past, higher accumulation rates presently. It could be due to a lot of factors, higher rates of productivity, less oxygen exposure now. Yeah, Christine?
Why did you choose